Hello. This presentation will cover exponential growth and decay. These problems are applications of the exponential and logarithmic equations that you've seen in previous videos. This video is published by the math department at Oakton Community College. So in all of these problems, we are concerned with finding the total amount of some object or some quantity of some product. So the total amount A, where A is the final amount, that some initial amount, A sub 0, grows or decays to after some time t, is given by this formula. So we have, let me get my pen, that A, again remember A is the amount at the end, is equal to A sub 0. So this is one variable. You can think of this as P, or the principal amount, multiplied by E, where E is a constant. So this is our exponential base, 2.718 ... raised to the K multiplied by T, where T is the time that's passed from the beginning to the end. So what's important to note here is K. K is called the exponential growth rate. So this one number, this growth rate, tells you what type of problem you're working with. If K is greater than 0, then you are working with an exponential growth problem. Whatever quantity you're measuring is growing at an exponential rate. If K is less than 0, then you are working with an exponential decay problem, which means that whatever quantity you're working with is decaying or dropping, getting less than at some exponential rate. And that exponential rate is K. So what's nice about these problems is that K will usually shake out, whether it's exponential growth or decay, based on the sign of the problem. So just keep in mind that K greater than 0, so this first one, positive, K less than 0, negative. So how do we work with these problems? What types of problems are we going to be looking at? Well, in our problems, we're going to have some scenario in which we have some quantity, and that quantity is going to get bigger or is going to get smaller, and the problem will tell us exactly how long it takes to do so and how much we have left or how much more we have. And then it will say, all of a sudden, find this. So it's our job to kind of pull all these pieces together and to compile not only a formula, but also the solution and whatever quantity the problem is asking for. So if we want to kind of lay out some steps or guidelines for this process, the very first thing you want to do is to find your exponential growth rate K. How do you do this? You can see these as two-step problems. The first part of the problem is going to give you an initial amount, a final amount, and a time. They're giving you all of your variables except K. And it's important to remember that E is not a variable. E is just going to hang out. And so once you plug all those numbers in, the only letter that will be left is K, and so you just have to solve for that K. Once you solve for K, you then write out your formula. And important to note, you write the formula with K as the number, because now that you know the number, you have the formula for whatever growth or decay you're working with. And then the last step, usually the problem will say, how long does it take this to happen? Or how much do I have left after this time? Or how fast does this populate? Whatever. So whatever quantity the problem is asking for, step 3 is find that quantity. So find the quantity asked for by the problem. All right, and so we have our guidelines, we have our steps. The best way to do application problems is to just jump into them. And so I have two word problems that we can look at here. The first is a population growth problem. So population growth is I almost said popular, that's ridiculous. Population growth is a type of, is an example of exponential growth. There are many different ways to model population growth, but one common way is to use an exponential growth model. So this problem states that in 2000, the population of a certain country was approximately 3.2 million, and by 2050, it is projected to grow to 12 million. Use the exponential growth model, in which t is the number of years after 2000, to find the exponential growth function that models the data. And then the question asks, in which year will the country's population be 9 million? All right, so let's note a few things here. First, we're talking about population, and so normally what I do when I'm trying to figure out my problem is I jump right into what are my variables. So we have a sub 0, we have k, and we have t. Notice I did not put e down because, again, e is not a variable. E is the base of our problem. So in 2000, the population was blah. In 2050, it's projected to grow to blah. And I think the most important place to start in this problem is that t is the number of years after 2000. And so just like that, start, end. When is our starting? 2000. When is our ending? 2050. And so it means that the number that we have in 2000 is the starting amount, a sub 0. The number that we have in 2050 is the ending amount, a. And so I can write down a is equal to 12, because that's the projected population in 2050. And I can write down that a sub 0 is 3.2, because that's my initial population, or the population, in 2000. K, who knows what k is? This is the start of the problem. Most of these problems, I won't say all because I haven't seen all possible problems, but most of these problems start off with solve for k. So k is, I have no idea, question mark. So then what is t? T is the amount of time that has passed. So if I've gone from 2000 to 2050, I'll give you a second, how much time has passed? Exactly, 50 years. And so now we use our formula. A is equal to a sub 0 e to the kt. And I put in the numbers that I have. So 12, actually, excuse me, let me do this. Let's use a different color. 12, because we're now solving for k, is equal to 3.2, because that's my a sub 0. E just hangs out. Raised to the k, I don't know what that is, times t, which is 50. And so now I have an equation, exponential equation, where k is my unknown. So how do we solve an exponential equation? Well, we watched the previous video, so we know that the first thing we do is isolate the e statement, isolate the expression. So I divide both sides here by 3.2. Now, I like to round at the end to make sure that I don't have any loose numbers. So I'm going to leave this fraction, this weird-looking fraction, as 12 divided by 3.2. So I have 12 over 3.2 is equal to e, I'm going to rearrange this, raised to the 50k. All right, pause. How do you undo e? How do you get rid of e? I hope all of you immediately had pop into your mind ln, because the only point of ln is to get rid of e. And so that means that if I do this next step, everyone wait for it, ln of both sides. Why am I lning both sides? Because I see e and I don't want to. So now I ln both sides, and ln and e, inverse functions, undo each other, and so I'm left with 50k, no more e. And on the other side, I have the natural log of 12 divided by 3.2. At this point, I'm solving for k, and so getting k by itself, divide by 50. K is equal to the natural log of 12 divided by 3.2 divided by 50. My writing has been better, I apologize for that. Alright, so due to the magic of my calculator, I know that this is approximately 0.026. I usually keep 3 decimal places, that's just me. I think my math lab asked for 2 decimal places. So if this were 2 decimal places, it would be 0.03. We would round to the hundredths place. So I have completed my first step. I have a quantity, an approximate value for k. My exponential growth rate here is 0.026. And what do we see? Positive, because I started at 3.2, I grew to 12, and so k is positive. And so I can now write that a is equal to a sub 0, 3.2, e base raised to the k, which is 0.026 t, because t is now anything. Any year I want to plug in for t, I get out the amount a in that year. So now we can skip to the next question, because we have found our growth function. This a equals is the answer to the first part. But now the question asks, in which year will the country's population be 9 million? So I'm solving for t there, and I want to know when it grows to 9 million. So in other words, a is 9 million, because I already know a sub 0. That never changes. I always start with 3.2. So that 9 million is now what I'm growing to. So I have 9 And you know what, just to keep this clear, changing colors, A is equal to 9. A sub 0 is still 3.2. K, because we have solved for it in the first part of this problem, is 0.026. And T is my unknown. I do not know when this will happen. What year does this happen in? And so I write out my numbers again. 9 is equal to 3.2 e raised to the 0.026 t. And so I once again have an equation, but this time instead of solving for k, I'm solving for t. But they're in the same place, so it's basically the same steps. We don't have to do anything new here. So I'm going to do this a little quickly, but it's a video, so if I go too fast, just slow it down. But I could divide by 3.2. And so then I have 9 divided by 3.2 is equal to e to the 0.026t. And once again, I have e. I don't want to see u. How do I undo e? If you were here, you would scream out, ln on both sides. And so I ln both sides. ln of 9 divided by 3.2 is equal to ln e, inverse functions. Undo each other, gone, 0.026t. Excuse me, I'm getting too excited. Writing's getting a little janky. So then I divide both sides by 0.026, divide by 0.026, and we have our answer. T is equal to this quantity, which is approximately equal. So T is approximately equal to 39.77. Okay, be very careful here, everyone. What are we writing down? 39.77 years past 2000, because T is the after amount. How much time has passed? So if we translate what that means, 2000 plus 39.77 years would be 2039.77. Now, if you were in front of me, I would ask you, what year is 2039.77? Okay, pause for dramatic effect, and then we see that doesn't make any sense. So we have to be in the year 2039.77 and some. And so that means that we're approximately in the year 2040. So you're like 3/4 of the year past 2039, which means you're into the year 2040. Okay, and so that's our answer. So we can now say that our growth function, A, is equal to 3.2 times e to the 0.026t, and that the population will grow to 9 million in the year 2040. All right. So that concludes this problem. I'm going to try and pan all this on the screen so we can see it all in one shot. And then we're going to scroll down and do it all over again. Because now we have a different problem. And so we have Xanax as a tranquilizer used in the short-term relief of the symptoms of anxiety. Its half-life in the bloodstream is 36 hours. How long will it take for Xanax to decay to 90% of the original dosage? So let's just kind of note one thing. The time in this problem is in hours. I'm not working in years. So T is not going to be convert 36 hours to years because I don't want to do it. It's too many fractions, it's too much. So we're just going to convert everything to hours, everything. So I do the same thing as before. What are my variables? A sub 0, K, T. Beginning of the problem, which means that I'm solving for K. So A is the original amount. Oh, whoa, excuse me. No, I'm not. Its half-life in the bloodstream is 36 hours. That means that I know exactly how long it takes for it to decay. K, so let's start this again. Pardon me, everyone. This is a half-life problem. And so it takes 36 hours for the amount to drop to 50% of the original. So what does that mean? So let's just take a second to realize what that means, because that actually kind of tripped me up originally too. Half-life says that if I start with this Xanax, no matter what amounts I start with, 36 hours later, I have 50% left over. And so if I go through my equation or my variables, A sub 0, K, and T, work this through. A is going to be, well, I don't know what A is. A is 50% of whatever I started with. So let's kind of just mess around here. What did I start with? I don't really know. I don't know. So let's just leave this as a sub 0. But then if a is 50% of the original, 50% of this a sub 0, well, what is of? Multiply. 0.5, 50% of a sub 0. And so we have a is 50% of a sub 0, 0.5 a sub 0. A sub 0 is, who knows what a sub 0 is? So just leave it as a sub 0. K, still going to solve for that. And t is 36 hours. So keep in mind, once again, that the time is in hours. All right. And so if a is equal to a sub 0, e to the kt, and then I will once again change colors here, we have 0.5 a sub 0 is equal to a sub 0 e to the k times 36. So everyone notice that we have letters everywhere. So let's just make sure we see what's supposed to stay and what's supposed to go. A sub 0 is a number. It's a constant. E is a constant. K is what we're solving for. 36 is a number. 0.5 is a number. And so E is going to be the same E as before. Whenever we want to get rid of E, we think of ln. Exactly. K is what we're solving for. So my final answer should be K equals. So the only letter I don't really want to see here is a sub 0. So how do we get rid of a sub 0? Well, where is a sub 0? It's on both sides of this equation. As long as I'm not starting with nothing. So let's just make sure we establish that. If you started with no Xanax in your bloodstream, 36 hours later, you'd have half of, wait for it, nothing left in your bloodstream. So 0 is just, we don't talk about 0. But if a sub 0 is not equal to 0, that means that I can divide both sides by a sub 0. Cross out, and I have only numbers left over. And so what do we see here? In those trick problems where they're talking about half-life, or when they're talking about percentages, they're actually easier than the previous problems because you never have to worry about the initial amount. It just divides away. 0.5, the percentage of the half-life, 50%, is equal to e to the 36k. Once again, I have e. I don't want to see e. What do? ln. And so I will take the natural log of both sides, natural log, and I have natural log of 0.5 is natural log and e, inverse functions undo each other, 36k. And so this tells me that k is equal to the natural log of 0.5 divided by 36. And if I want that approximation, this is approximately equal to negative 0.019. Negative. Why does that make sense? I started with a certain amount of Xanax. Let's say, I'm about to betray here. I am not a pharmacologist. So we start with some minute amount, let's say 100 micrograms. Hopefully that's not ridiculous. Bear with me if it is. So we start with 100 micrograms. 36 hours later, I have 50 micrograms. I do not have 150 micrograms. I have 50 micrograms. I went down. And because I went down, K is negative. Okay, so we've established that K is negative. And so if I write my formula, I have A is equal to A sub 0. I still don't know what that is. So I'm leaving it as A sub 0 because A sub 0 is A sub 0. E raised to the K, which I know as 0.019 negative T. All right. And so now we're ready for the second part of the problem. How long will it take for Xanax to decay to 90% of the original dosage? 90% of whatever I started with. Nowhere in this problem did they tell me what I started with because they don't have to. You're working with percentages, which means you're working with relative amounts, and so things divide away as necessary. A sub 0, K, T. So A is 90% of the original, and the original is A sub 0. So if A is sub 0 is A sub 0, don't know what that is, think 100, then A is 90% of that original, which is 90% of A sub 0. 0.9 times A sub 0. K, we know, negative 0.019. T, I do not know because I want to solve for how long, time trigger, how long will it take me to get to 90%? All right, so let's put these numbers in. So we have 0.9 a sub 0 is equal to a sub 0 e to the negative 0.019 t. Once again, what's on both sides with the equal sign? A sub 0. Divide by a sub 0, divide by a sub 0, and we have 0.9 is equal to e to the negative 0.019 t. And so now when yeah, you're just saying all of my emails. So now when I take the natural log of both sides, because I want to get rid of e, yeah, it's too hard to edit this out. You're just going to see everything, everybody. We're just going to see everything. So we have L and E undo each other, and we have negative 0.019t is equal to the natural log of 0.9. And so now when I want to get t by itself, divide by negative 0.019, divide by negative 0.019, and t is equal to natural log of 0.9 divided by negative 0.019. And this decimal approximation is approximately 5.545. Keep in mind this problem is in hours. So this says after approximately 5.5 hours, we would have 90% of the Xanax left in our system. Pause for all of my pharmacists, all of my pharm techs, for all of my aspiring pharmacists. Why do you need to take this class? This just happened. Just keep that in mind. This is why. Because then you refine this in calculus. This is why. All right. If you have any questions, please contact your teacher. And I hope that this makes sense. And I wish you all luck on your future coursework.